So good evening, all of you. In my video lecture series, today I am going to give talk on the topic theory of chemical kinetics. So chemical kinetics, as far as we consider, and that are the branch of chemistry which deals with the study of reaction rates and their mechanism called chemical kinetics. Reaction rate means change in concentration per unit time. Suppose we starting with 10 mole of the reactant and 5 mole reactant converted in product in suppose 5 minutes, then rate of reaction will be 5 by 5 means 1 mole per minute. So by that way we can determine. So change in concentration of either reactant or product per unit times. Now, as we know that the thermodynamics tells about the feasibility of the reaction, means reaction is possible or not, that may take place or not. And whereas chemical kinetics tells about the rate of reaction, means if reaction taking place, then in which rate, in what rate that can be converted into the product. Okay. So, for example, thermodynamic data indicate that diamond shall convert to graphite. This reaction is possible. Diamond may convert, shall convert it to graphite, but in reality, the conversion rate is very slow, and that the change is not perceptible at all. So, because that are very too slower reaction, so time taking for reaction is very long, and that means 1 mole of the diamond will take long time to convert into graphite. And once you divide that change in concentration by the time consumed, then value we getting that almost negligible. So that almost meaningless. But thermodynamics said that the reaction is taking place. Reaction should be happen. But in what rate, that is not practical. Practically, that not possible to determine. So chemical kinetics related with the rate of reaction. Now kinetics studies not only help us to determine the speed or rate of chemical reaction, but also describe the conditions by which the reaction rates can be altered. There is a lot of factor that influencing the rate of reaction, like temperature, concentration of reactant, then catalyst. Lot of factor is there. So along with the rate of reaction, it also the factors which are associated with chemical which influencing the rate of reaction is also we have to discuss in this one. But the factors such as concentration, temperature, pressure, and catalyst affect the rate of reaction. Now, rate of chemical reaction. Rate of chemical reaction is the speed of reaction or the rate of reaction as the change in concentration of reactant or product in unit time. And it can be expressed in terms of the rate of decrease in concentration of any one of the reactants. Suppose if there is a multi-reactant reactions, then with time, as we know that when reaction proceed, amount of concentration of reactant that decrease with time. So their rate, in what rate that decreases, from that we can get the rate of reaction with respect to particular reactant. And also, if there is one or more than one product may be formed, and with time, concentration of product that increases. So the rate of reaction is defined as in the increase in concentration of any one of the product in the given chemical reactions. So by any means, either you can determine the rate of decrease in concentration of any reactant. If there is one, so there is no problem. If more than one, then you can estimate this one by considering any one of the reactant taking part in the reaction. And secondly, or you can consider the rate of increase in concentration of one of the product. Now, Consider a hypothetical reaction, assuming that the volume of the system remains constant. So suppose R denotes suppose reactant and P is product. So any reactant is product. This is unimolecular reaction. Here one reactant converted into product. So R reactant converted in product. Then suppose if 1 mole of the reactant R produces 1 mole of the product P. Now, if the R1 and P1 are the initial concentration of reactant and product respectively at time T1, and R2 and P2 are their concentration at time T2, then changes in time, that means time consumed for the reaction is del T, that given by T2 minus T1, and changes in concentration of reactant with that time, during that time is R2 minus R1 denoted by del R, and changes in concentration of product, that is del P, is equal to P2 minus P1. Concentration of P2, and P2 is final concentration, P1 is initial concentration. So differences in final concentration and initial concentration of reactant or product, that is we determine. Then by using these two, time and concentration, we can determine the rate of reaction, then rate of chemical reaction. If you consider suppose reactant, then with time that reactant disappears, their concentration decreases, then the rate of disappearance of reactant is equal to decrease in concentration of reactant concentration divided by time taken. So final minus initial, so that is minus del R by del T. Negative sign here indicate that with time the concentration of reactant that decreases. And with respect to product, rate of appearance of product P is equal to increase in concentration of P divided by time taken, that denoted plus del P by del T, where plus sign indicate there is an increase in concentration of product with time. Now, since del R is negative quantity, as concentration of reactant is decreasing, it is multiplied with minus I to make the rate of reaction a positive quantity. Now, theories that are the main topic today's. Our main topic, main focus is on the theories. So, theories of chemical kinetics. There is mainly two theory is related, associated with the chemical kinetics. One is collision theory, another is transition state theory. Okay, let me discuss one by one. So, collision theory means collide. So, reaction occurs when reacting species have sufficient energy to collide and proper orientation is space. Now, why we using this term sufficient energy? Actually, when we taking two reactant or any one reactant, if we taking reactant for a particular reaction, then we know that suppose if we using glucose, trying to convert glucose into fructose. So glucose is most stable in nature. Most stable means that are non-reactive, that do not taking part in the reaction. So if that do not take part in reaction, then there is no fructose formation. So to get that fructose, first we have to activate, unstabilize, or to convert that glucose in reactive form. And the reaction, if you consider thermodynamical concept, then this stability is mainly depends upon the internal energy. If internal energy of any compound or molecules or element is less, that consider more stable. So in stable state, suppose if you consider glucose, in stable state, glucose internal energy is less. Now, if you try to activate that one, for that, we have to increase their internal energy. How can we increase? By supplying sufficient energy from outside. Once the internal energy reach at certain level, then that becomes activate and then that participate in the reaction that involved in the reaction. So before starting reaction, it is essential to increase their energy up to a certain level, sufficient energy, then that collides with other reactant in proper orientation in space. Now here proper orientation means when the two reactants interacting, then that interact at a specific site in a specific condition in a specific orientation. So before collision, they attain a proper orientation in space. Okay, then with sufficient energy that collide in proper orientation, then that able to react and giving a product. Here one term is comes that is called energy barrier. That term as we have used sufficient energy that related with the energy barrier. So what is energy barrier? So energy barrier is actually the minimum energy which the colliding particles possess in order to bring about the chemical reaction is called threshold energy. Means, suppose if any reactant, again, if we take example of glucose, if we using glucose as reactant, their internal energy is, if you try to convert that one in product, then it essential, it is important to increase the internal energy of glucose up to a certain level. Once that reach at certain level, then that able to convert into product. So that level of energy, that minimum energy, that glucose molecules required to reach that maximum, that minimum energy levels, that is called threshold energy. So once the reactant molecules reach their threshold energy, when their internal energy reach up to threshold energy, then that able to give product. So that energy level, that means when we saw this one transition state theory when we discuss, then that will be clear. So when that reach up to that level, then that able to, so that level, that layer is called energy barrier. Okay, so that will be clear from the graph. So the energy difference between threshold energy and average energy of reacting molecules is called activation energy. Now, another is orientation barrier. As we have said that if you, as far as we consider collision theory, then for collision there is two things is necessary. One is sufficient energy level and second is proper orientation. So for second sufficient energy level that should be reach up to threshold level. For up to reach up to threshold energy level that needs some additional energy. That additional energy needed to reach up to threshold energy is called activation energy. And second thing is that is their proper orientation. So once that reach their proper orientation, then that able to collide. If there is no orientation, then there is no collision. So that is called orientation barrier. So one is energy barrier, another is orientation barrier. That said, colliding molecules should be in their proper orientation at the time of collision. Now, second theory that actually both are interrelated. Collision theory on the basis of that collision theory concept, this transition state theory is given, and it said that in the activated complex theory, activated complex means when a reactant taking part in reaction that first forming a complex. And that complex actually reach their energy level reach up to the when that forming complex, then they reach up to the threshold level that is called activated complex. So in the activated complex theory, we consider two reactant approaching and their potential energy rising and reaching maximum. So if you see this graph, then from this graph, if you on x-axis reaction coordinates and on y-axis if you take the energy level, then if you see here this part if suppose in any reaction, one of the reactant is A, another reactant is BC. Means A reacting with BC and giving product AB and C. Okay. So when this A reacting with BC, so A has their internal energy, B plus C also has their internal energy. A and BC interacting in proper orientation, that interact forming complex, and now when that forming a complex, then their total internal energy sum up, and that total internal energy, suppose up to this one on y-axis, this is their internal energy. Okay. Now when you try to convert this reactant into this product, then as this A and BC both are stable, so to convert that one into product, first our target is to activate that one, convert that one into reactive form. For that, we have to increase their internal energy. We have to supply energy from outside sources to increase the energy level of the complex. And once their energy level reach up to the certain level, a minimum this one, suppose this level, once that their internal energy reach up to this peak line, this line as we see here, once their energy reach here, then that able to convert into product. So this energy, this total energy, this whole energy, this energy is called threshold energy. Minimum energy required to convert into the product. And this layer, this level, this one, this layer, this is called energy barrier. Barrier means once that cross, so if that energy level remains lesser, then that unable to convert into product. Once that cross this energy level, then that give product. So this is called energy barrier. So you can define threshold energy also as the total energy, the maximum energy needs to cross the energy barrier is called threshold energy. Now, once that converted, once that reach their threshold, once that cross this layer, then that able to convert into product and giving the product. Now, from graph, you can see this A plus BC complex already has their internal energy. Now, this additional energy we supplying from outside. Now, this energy, once we supply this energy, then that activated reach up to threshold. So, this energy, this amount of energy, additional energy needed to cross this energy barrier is called activation energy. Okay. So, activation energy is the energy, minimum energy required, minimum energy absorbed, minimum energy supplied. Cross the energy barrier is called activation energy. Once that cross this energy barrier, then that converted into product and giving product. Okay. Now, in reaction, if you apply thermodynamical concept, then we know that reaction is of mainly three types: exothermic, endothermic, and isothermic. So here in this example, you can see this A plus B has this amount of internal energy, but when that converted into product, the product internal energy is lesser than reactant. So the absorbed energy means active additional energy that absorbed, that is activation, is that really during this conversion. Besides that, additional energy, this also released. So ultimately, when we write overall reaction, then in that one we can see during this reaction some amount of energy released. And as the some amount of energy released, so this one is exothermic reaction. Again, if that absorbed, then endothermic. If there are no loss or gain, then that remains isothermic. But in this example, we clearly see that after completion of reaction, some amount of energy releases. So this one is exothermic reaction. No, so here del H is equal to EA minus EA dash. So that means so activation energy is the energy needed to form activated complex is called energy of activation. It is very low for some reaction and very high for others. Now, the rate of reaction is directly related with this activation energy. If there is an activation energy need in more amount, that take long time, and if that take long time, reaction rate slow. And if that required less amount of activation energy, less amount of energy to supply, then that energy we will supply less time. If time lesser, then as we know, rate of reaction is inversely proportional to time. So if time consumptions decrease, rate of reaction increase. So there is some points that are associated with activation energy. Activation energy is always positive because in any reaction, if you try to activate any reactant, that should absorb heat. So activation energy is always positive. Larger the value of activation energy, slower the rate of reaction at a given temperature, because that needs more time to supply that energy, that need more time to cross the energy barrier. So, and if time consumption increases, rate of reaction decreases. Just reverse, the larger the value of activation energy, the steeper the slope, ln k versus 1 by t. A high activation energy corresponds to a reaction rate that is very sensitive to temperature. Now, effect of temperature. Now, for a chemical reaction with rise in temperature by 10 degrees centigrade, the rate constant is nearly double. It has practically seen that for particular reaction, if you increase the temperature by 10 degree, then their rate of reaction becomes doubled or tripled. Generally, that becomes double. So that is expressed by, so if you consider temperature coefficient, it is the ratio of this. You can see k t plus 10 divided by k t. Whereas kt is rate constant. We know that rate of reaction is directly proportional to rate constant, and rate constant is directly depend upon temperature. So if Kt, suppose if Kt is the rate constant at temperature T and Kt plus 10, that means this is the rate constant when we increasing the temperature by 10 degrees centigrade. So the ratio of this one is called temperature coefficient and its value is 2 or 3. Generally, it's 2. Now, this effect of temperature on chemical kinetics, that is that determined by a specific equation that is called Arrhenius equation. The temperature dependence of the rate of chemical reaction can be accurately explained by Arrhenius equation, and the Arrhenius equation is K, where K is rate constant equal to A E raised minus EA by RT, where A is frequency factor or Arrhenius constant, EA is activation energy, or you can simplify that one in the form of logarithmic form, that is ln k equal to minus EA by RT plus ln A. Now, if you plot a graph between log k versus 1 by 10, then we can get a straight line with negative slope, which value minus EA by 2.303 R. Okay. So, like this one. So, if we see this graph, if you plot graph between from Arrhenius equation, if you plot graph between ln k and 1 by t, then we see here the graph is negative and their slope is equal to minus EA by R. Okay. So, this is the dependency of the chemical reaction on temperature. So, plot of ln k versus 1 by t is straight line and slope is minus EA by RT. Minus sign indicate the slope is negative. So, at temperature T1, suppose at temperature T1, the rate constant value K1, then equation becomes ln K1 equal to minus EA by RT1 plus ln A. Equation 1. And at temperature T2 means if you increase temperature, if T2 is greater than T1, then ln K2 equal to this one. Then where K1 and K2 are values of rate constant and temperature T1 and T2 respectively. Now subtracting equation 2 from 1, we can get by this way ln K2 minus ln K1 equal to EA by RT minus R2. Solving this one, we can get log K2 by K1 is equal to EA by 2.303 R in T2 minus T1 by T1 minus T2. Now this will be also shown by the graph. So suppose if T2 is greater than T1, then you can see this height of this energy barrier at temperature T1 is more. So if energy height is more, that means the activation energy needed is higher. And if activation energy more, rate of reaction slow. And if you increase temperature, then you can see this peak decreases. That means height of energy barrier that decrease. And as the height of energy barrier decrease, activation energy value decreases. And if activation energy value decrease, rate of reaction becomes faster. So that will be explained by this graph. And or also you can finally write this that equation as log K2 by K1 equal to EA by 2.303 R into 1 by T1 minus 1 by T2. Okay, so one of the factors that influencing rate of reaction is temperature, another catalyst. So catalyst is a substance that change the rate of reaction, either that increase or decrease. So change the rate of reaction without being consumed in the reaction. That means that remains unaltered, that remains unchanged after completion of the reaction. That only helping in the reaction. That do not initiate the reaction, that do not alter the chemical equilibrium, that do not alter any thermodynamical values, each and everything. Okay, but that only either enhance, generally that increasing the rate of reaction, but in some cases that decreasing also. So in case when that increase the rate of reaction, then that is that considered as positive catalyst, and if that decrease the rate of reaction, then that considered as negative catalyst. So catalyst function is that one that provides an easier way to react, lower down active. This is the most important this one by which this catalyst is work. Catalyst actually doing that, actually decreasing the activation energy. And as we know when activation energy value decrease, rate of reaction increase. So this catalyst actually decrease the activation energy value, still make the same product. There is no change, no effect on any nature of the changes, nature of the product. Nature of product remains same, either in presence of catalyst or in absence of catalyst. Enzyme, if we consider, that is called as biocatalyst, because enzyme function is similar as the inorganic catalyst inside the living organism. Okay, so enzymes are biological catalyst. Besides that, another inhibitor that is also called as negative catalyst, that substance which decrease the rate of reaction is called negative catalyst. Now, how catalyst change the reaction rate? So actually, as we said that actually decreasing the height of energy barrier, that decreasing the activation energy. So if we see here this example from this graph, so if chlorine ozone and oxygen, if that taking part in the reaction, suppose this is the internal energy of this all, then energy on axis. So in absence of catalyst, see this red line. This red line indicates that here their threshold reach and the activation energy value is this one. Means once this gets, so this EA is the uncatalyzed reaction, this activation energy, this EA is activation energy when in absence of catalyst. So if you see this one, their range is this. This is the height of energy barrier, and this is the amount of energy consumed due to for completion of the reaction. So this is the activation energy in absence of catalyst. But when you apply catalyst, then practically seen that their height decreases. That means the amount of this activation energy that is. And as the amount of activation energy decrease, time consumption that decrease, and if time decrease, rate of reaction increase. So by that way, so this catalyst actually that decreasing the height of energy barrier, or you can say that decreasing the activation energy. No, so catalysts are the one way to lower the energy of activation for a particular reaction by altering the path of the reaction. The lower activation energy allows the reaction to proceed faster. Now, a mechanism is a collection of elementary steps devised to explain the reaction in view of the observed rate law. Now, if you say consider the chemical reaction, then is two kinds of chemical reaction: elementary reaction and non-elementary reaction. Elementary reaction means that reaction which completes in a single step. Okay, so in single, when that if you get a product in single step, then there is no any problem. But if reaction proceeds in more than one step, reaction completes in more than one step, then it's very difficult to choose the step for determination of rate of reaction. Okay, so in that case, we considering actually, just say for the reaction to NO 2 plus F2 to give 2NO2F, then rate law we can write in this way. And can the elementary reaction be the same as the overall reaction? If they were the same, the rate law would be have been rate K this one. But their rate of rate law equation is actually practically that are equal to K, and but if you see the reaction, from reaction if you write the rate law equation, then that should be K NO2 power 2. So because their coefficient in given chemical reaction is 2, but actual in rate of reaction there is an that not mentioned. That means what? So if you remember order of reaction, then from this equation the order of reaction is 2, but from this reaction order of reaction is 3. So why this differences is taking place? As this reaction is not complete in single step, that completed in several steps. So we considering the step from which we can write the rate law equation, or we can determine the rate of reaction. Therefore, the overall reaction is not an elementary. If that are elementary, then there should be rate of equation is this one. As this one is not elementary, so practically rate law. How this one is taking place? Now, so rate determining step, generally, if you consider chemical reaction, then there is generally three kinds of reaction. Very fast reaction, slow reaction, very slow reaction. So fast reaction, in fast reaction, what happens? If you add reactant, that reactant convert into product very fastly. That means time consumption is very less. Now, if you divide big quantity by less quantity, big concentration by the less time, then that meaningless. Again, if reaction is too slow, very slow, then again what happens? That take long time to get a 1 mole of product. So we getting suppose 1 mole product, but that need more time. So if you divide that one with time, almost negligible value you can get. That should be meaningless. So for rate determination, we choosing generally slower step. Okay, okay, medium, moderate step. That which complete in moderate time. Okay, so that slowest step is considered as redetermining step, which is a step in a mechanism, and the rate law for this step is the rate law for the overall reaction. Now, steady rate approximation, the steady state approximation is general method for the deriving rate laws when the relative speed cannot be identified. It is based on the assumption that the concentration of the intermediate is constant, and so this is the last of our topic, today's topic discussion. Again, there is a lot of things is remain in this heading, not possible in a single this one. So we will discuss the related things like order of reaction, molecularity of reaction, first order, second order, zero order, then half life, full life. We will discuss that one in our next lecture. Till now, Thank you.